Okay, in this problem we have a rotational motion problem. This problem is to draw attention to the relationship between rotational motion and translational motion. Here we have a solid ring. Here we are told that it is turning with constant angular acceleration, and we have a couple of points on that ring, point P and point P prime. Point P prime is actually the same point P that has moved in a circle. So essentially over time, point P has become point P prime. And in part A, we're asked to calculate the magnitude and direction relative to the x-axis shown. Right, we have our coordinate system shown here. And okay, so the magnitude and direction of the translational acceleration at that point P at time t equals t naught. All right, and we want to draw a sketch of the vector on the figure below. Okay. All right, so at t equals t prime, this system is starting from rest. Okay, so we have it's rotating counterclockwise at t with constant angular acceleration. Okay, so we'll put here for clarification. Let's see, does it say it anywhere? So for clarification, the system starts from rest. All right, so we're going to use a little bit of knowledge here about rotational kinematics, basically the equations of constant angular acceleration. Exactly. Okay, so for clarification, the system starts from rest. And that tells us that at t equals t naught, omega equals omega naught equals 0. All right, so there is no angular velocity at that point. Basically, the disk is just starting to move, but it hasn't started the move yet, right? So it's starting from rest, and then it's going to speed up over time, and it's going to get faster. But initially, it's not in motion. Okay, so does that mean that there is no acceleration? Well, no, there is acceleration, because the key thing about translational acceleration is it's got two components. So translational acceleration, as a vector, has a radial component and a tangential component. Okay, so it's key to understand that translational velocity has two components. And of course, we've been talking about translational acceleration in previous chapters up until this first chapter on rotation. And we maybe didn't think about it having these two components, but these are the two components that are specific to rotational motion. And up until now, the only type of rotational motion that we've discussed has been uniform circular motion. Well, uniform circular motion is defined by the fact that the speed of the translational velocity is constant, which is to say that the acceleration is also constant in magnitude, and it is only the centripetal acceleration, which now we're calling the radial acceleration. So let's add that as a note. For uniform circular motion, the translational acceleration is only equal to the radial part. Okay, because the tangential part is 0. And I'll say since since AT is by definition dv dt, and if, or I should say, delta v, the change in velocity over the change in time, well, notice that's the magnitude, right? This is the magnitude of the velocity. In other words, the speed. So if the speed isn't changing over time, then it's 0, right? If the speed is constant, right? Because it's a uniform circular motion. Okay, and the magnitude, AR, is the same as what we call the centripetal acceleration, and it's just v squared over r. So that's what we've seen before as far as translational acceleration is concerned for rotational systems. But now we're having a system that isn't uniform, right? This is a non-uniform circular rotation, right? It's non-uniform rotation. So let's say, but this ring is rotating non-uniformly. And all that means, right, all that term means, non-uniformly, so we'll say so, that means that AT does not equal 0. The tangential component of velocity does not equal 0. Okay, so just to add, right, so I'll add the terminology over here. I'll just label these. So this is radial, and this one is tangential, right? Because I wrote the subscripts R and T, but I want to have that in writing on our notes here. Okay, so let's go ahead and actually answer part A with a little bit of with that background out of the way. Okay, so here I've drawn a couple of axes in green on our figure, this being the tangential axis, okay, so and that's at point P, because the thing is that the tangential and radial axes, they move with your point, so they're going to move around the circumference, and we're looking at different points along that circumference. But at this location, which we care about for part A of this question, then these are the axes. So in other words, we see that the tangential axis is parallel to the y-axis, and the radial axis is parallel to the positive x-axis. That won't always be the case, but that is the case at point P. And since our system is starting from rest, and it hasn't started moving, the only component of the translational acceleration is the tangential component. So then I've shown here that then the tangential, or rather the translational acceleration, A, well, it's just at P, right? So A sub P is simply parallel to T. Okay, and now let's see what is that value? How do we actually calculate it? Because you know that's its direction, but what is its magnitude? Okay, so here I've shown our calculation steps. So going, right, so what do we want to do? Well, the good thing to consider, important thing to consider about these two components, the tangential and radial components, other than the fact that we can think about their definitions in terms of translation, this being that the tangential component is the change in speed, and the radial component is the centripetal. So those are the effective ways of thinking about them, and up till now. But now we also want to relate them to rotational variables as well. And that's what these equations are showing here, is the tangential component of translational acceleration, by definition, is alpha r. It's simply the angular acceleration, alpha, times the radius. In this case, since our point P is along the radius of the ring, it will be the full radius. If we were looking at some other point that was somewhere in the middle, then we would have a different radius, right? So we could have some some r prime, for example. But in our case, the distance to P is the full radius of the ring. Okay, and furthermore, we've got, so that's the tangential component, and then we also have the radial component. Well, here I show that it's all what its relationship is to translational velocity, but this is its relationship to angular velocity, because v is omega r in the same way that a sub t is alpha r. So then we make that substitution, and we see that one of our r's cancel, and so then we get that the radial component of translational acceleration is omega squared r. Okay, so these are our two key equations that relate translational and angular accelerations. Okay, all right. Well, since we're starting right initially at t equals 0, omega equals 0, then we can say, okay, well then if we want to fully calculate a, which is what we're asked to do in part A of this question, then we'll use the Pythagorean theorem to consider the two components, the translational and radial components, square them and put them inside the square root. Okay. Well, since AR is just equal to 0, since omega equals 0, then we're just going to have the square root of a sub t squared. So then the square root and the square cancel out. So we just get that a is simply equal to the tangential component, which I show over here. Okay, and then its value, well, it's simply alpha times r, which is just going to be 5.6 times 2, because 2 is the radius of our ring. So we get that at t equals 0, the total translational acceleration, which points entirely in the tangential direction, or the positive x direction, has a magnitude of 11.2 meters per second squared. All right, and so in here I say that the direction, that is 90 degrees relative to the positive x-axis. Right, so basically that this right here, this angle is 90. Okay, all right, so that is part A. Let's move on to part B. Okay? So in part B, we're asked for what's happening at point P prime. So basically once the ring has rotated through half a full rotation, right? Because we've moved from here to here. And in that time, the ring has been rotating with a steady angular acceleration of 5.6. So it's speeding up its rotation, which means that by the time it gets here, omega is no longer equal to 0. It certainly has a velocity. Like the wheel as a whole has a velocity, and since that's the case, that we're going to see that we must have a non-zero radial component of translational acceleration, which is to say that our centripetal acceleration is non-zero. And of course, if a person was standing here, they would now experience a non-zero centripetal force. Okay, whereas here the centripetal force would be 0 at point P. Okay. All right, so we're basically going to not have to go through all the background steps because we've explained how we calculate this. So let's just jump into the formula here, which is just going to be finding the total translational acceleration as the sum of the squares inside the root. Okay, so the radial and tangential components. Okay, well, they're both non-zero. Okay, so go ahead and make that calculation. Okay, so AT, well, that's still going to be alpha r squared. So that hasn't changed. Now AR, well, we know that's omega squared r. So we're going to have omega squared r squared. Okay. And how do we find omega? Well, we have to use the kinematic equations of constant angular acceleration to find omega. So I'll put that here as the next step. And omega is going to be omega naught plus, omega naught squared, plus this one, and then 2 alpha delta theta. Okay, so this is one of the kinematic equations of constant angular acceleration. This is the one that was that in translational form used to be v squared equals v naught squared plus 2a delta x, for example. All right, so obviously we've just changed all the a's to alphas, the x's to thetas, and the v's to omegas. And it's the best fit for this particular question because we don't know how much time, we could find out, but we don't need to know how much time it takes to go from P to P prime, or for P to become P prime, but we know the actual angle that's covered, which in this case is going to be pi, right? Because it goes a distance of pi from here to here. Okay? And it all has to be in radians. All these equations, everything for rotational motion has to be done in radians. Okay? So then we're going to get that omega is going to be the square root of, well, this one, omega naught is 0. Okay, so it's just going to be 2 alpha delta theta. Okay. And, okay, which we'll go ahead and find value for that. So it's going to be 2 times 5.6 radians per second squared times pi. Okay, looks good. All right, let's go ahead and calculate that. Okay, so if we actually plug in our value here, let's do a square root. Okay, and we have 2 times 5.6 times 5.6 multiplied by pi. All right, looks good. All right, so 5.93 is our angular velocity at this point. 93 at point P prime. 5.93 radians per second. Okay, so then we can go ahead and plug in everything to find our total translational acceleration. Okay, so we'll go back to the equation above, but you plug in numbers. Okay. So what is that going to look like? Well, we're going to have our alpha r. Okay, well, we actually already know that alpha r is 11.2, so that hasn't changed. So I can just go ahead and plug that in. 11.2 radians or meters per second squared. Okay. And then that's going to be squared. Okay. And then we're going to have our 5.93 radians per second squared, right? Because we're squaring the squared in this case, multiplied by our radius of 2 meters. And then that's all going to be squared. And then the sum of those two expressions is going to be inside the root. Okay, so let's do that on the calculator. All right, so this 11.2 already had, actually, no, there's no rounding there, so we can just keep it as is. Okay, and then plus, okay, open parentheses. This one I want to take completely unrounded. I'm going to square it. All right, multiply that by 2. Okay. Close that set of parentheses, square that term, and then finally close the root. All right, so I get 71. All right, 71.3. 71.3 meters per second squared. All right, so the units are not in radians or anything because this is a translational term. All right, that's we basically did the conversion from rotational expressions to translational expressions. All right, so now we know that's its acceleration. It's sped up, okay, or it's accelerating faster. Well, that makes sense, right? Because it didn't used to have a centripetal component, and now it does. And the radial component of the translational velocity is unchanged. So basically all we've done is just added a component to it. And notice that since the radial component is unchanged, that it quickly starts getting overwhelmed or sort of washed out by the effect of the centripetal component. Because we see that the centripetal acceleration is just constantly growing, right? This right here, this is the centripetal acceleration. Oh, I misspoke a second ago. The tangential, I was saying radial, but the tangential acceleration is quickly getting overwhelmed in magnitude by the radial acceleration, both being translational, right? A lot of terms here, and that's just going to continue to be the fact that value will just continue to grow. Okay, and we can see here that that this it would still be 11.2, and we have 71. So really 60 meters per second can be contributed to the radial component, right? Which now is obviously much larger than the tangential component, both of translational acceleration. And to really highlight this, we'll show the angle, right? The angle will show visually that the radial component of acceleration is so much larger than the tangential component. So I've added the same type of axes, the tangential and radial axes that I added at point P, but I've added these at point P prime. All right. Notice that the tangential axis now points in the negative y direction because it has to be tangential to the motion. Well, this whole wheel is rotating counterclockwise, so tangential to the motion would point down by the time that we get to point P prime. Okay, and here I'm showing the overall translational acceleration. That's right here, right? So this vector right here has magnitude 71, and I tried to draw it more or less to scale. So it's about 7 times longer than the acceleration vector we had at point P, and it's sub point P prime to tell us it's at point P prime. And here are the two components of it: the radial component and the tangential component of our total translational acceleration. Right? Because now they're both non-zero. Right? There is a non-zero radial component, and it's bigger, right? And here, and also it's not perfectly to scale, right? This part isn't, at least, because here I'm showing the tangential acceleration as being fairly long, and this one not being, quite 6 times longer. Okay, but regardless, all right, we don't need to show the radius right there, right? Because that value is actually not equal to 2 meters, right? If we wanted to show the radius in the figure, we could do it here. Right. That's our radius r. Okay. So, but moving on, we want then to find the angle. We're asked for the angle that this, okay, so let's see, the magnitude of point P, new location, aster has been displaced by radians. I say that it takes 1.06 seconds, which we don't need so much. And then we want to sketch this vector on the figure below, calculate the magnitude of point P, new location has been, Okay, so it just says calculate the direction and magnitude of A. Well, we'll stick with giving the direction relative to the x-axis because that's the way we gave our last angle, which was 90 degrees. So we want then to report the angle that the total translational acceleration makes with the positive x-axis, which is not the one shown here, right? So this one's going to be useful because we can use inverse tangent to calculate it, but then we have to remember to actually add that or find an angle that is relative to the positive x-axis. Okay, so let's go ahead and calculate theta. All right, so theta is going to be tangent inverse of opposite over adjacent, which is just going to be AR over AT. Okay, so let's see. So our AR term, that is the 5.93 squared times 2. Okay, so let's actually go back to the calculator and just find what that is. Okay, so 5, it's going to be this expression here, unrounded again, and then times, that does need to be squared, because it's going to be omega squared, or angular velocity squared, times 2 is, because the radius is 2, is going to give us the radial component of translational acceleration. So sure enough, it's 70. Okay. Shouldn't be quite 70. Oh, no, I guess that does make sense. Yeah, because exactly, it's 70 and 11. Okay, because basically it's the overall magnitude is 71, so it's not too much longer than this side, but then the tangential component is still going to be 11. Okay, so let's put this in. All right, so tangent inverse of 70.4. All right, so 70.4 meters per second squared. Okay, and then divided by the tangential component of translational acceleration, which is still 11.2 because it doesn't change. It's not time dependent, okay, or distance dependent. All right, so then we actually take that inverse tangent. Okay, so we want 70, because that's opposite, divided by 11.2. Okay, close parentheses. All right, so it gives us an angle of 1.4 degrees. And that's part of the reason I didn't draw this to scale in the figure, because it would basically just look like a straight line, right? Because the idea is that this angle right here is very, very small. And so it's pointing almost entirely in, I think I have it. I switched things, right? Okay, so let's do this, because it won't be one. You'll see it's almost 90 degrees instead of being almost 1 degree. Okay, almost 0 degrees. All right, so let's do it again with the correct value in the numerator and the correct value in the denominator, because I switched the order. So it should be 11.2 divided by 70, not the other way around. Okay, because it's opposite over adjacent for tangent. Okay. So, all right, and then let's change our mode here to degrees. And you might be like, well, why are we changing to degrees if this whole problem is in radians? Well, yeah, that's fine, except that I still want to think of the directions in terms of degrees. And yes, the kinematics of radial motion has to be in radians, but there's no reason we can't still think of a right angle as being 90 degrees. It's also pi over 2 radians, but we can definitely switch back and forth. Okay, as long as we're aware of when we do so. All right, so we get 9 degrees is our angle, and that makes sense. Okay, so we get 9 degrees, 9.04 degrees. Okay, that's our theta. And obviously this looks more like 45, right? But it'd be much less, or much less steep. Okay. Oh no! Oh, I see now. I had it correct the first time. All right, because it is the radial component is 70. It was the fact that it was in radians that threw me off. So let's do this. Okay, so that's 80 degrees. So in other words, this 9 degrees is, I'll show what that angle is. That would be this angle right here, which we're going to need anyway. So we'll call that one phi. Okay, and so make that a little bit larger so we can see it. There we go. Okay, so but the angle theta, as shown in the figure, is not 9 degrees. It's actually 80. So let's do this. Okay, 81.0 degrees. We're sticking through 3 sig figs. All right, but relative to the positive x-axis, right? So that would be if we were to take this vector, all right? So let's go ahead and move it over to our origin on the xy system, so I can show you what the angle is relative to the positive x-axis. So I've just moved our total translational acceleration vector over, and then I want to show, so the angle that's asking for, we'll call that beta, all right? So this angle right here, beta, is going to be 180 plus phi, okay? So you still see everything? Doug? Looks good. So beta is 180 plus 90 minus theta, which is the same as 180 plus phi, okay? And we already inadvertently calculated phi as 9 degrees, because that's 90 minus 80.1, okay? And so that's going to give us, for the angle relative to the positive x-axis, all right, so it's 180 plus our 9 degrees. All right, 189 degrees. Okay, so that's this one's 90. So basically, our angle initially at point P was 90 degrees for the translational acceleration vector, and then over time it turned this way and is now pointing in the third quadrant, right? So it's turned to more than 90 degrees, and now it's pointing down that way. And it will continue to turn, right? It's constantly turning, and it's constantly going to be growing, right? Because this value here, the radial component of the translational acceleration, is constantly going to be growing with distance and also with time, and it's just going to get bigger and bigger, which also means it's just going to become more and more of a vector that just points towards the center. Because what's eventually going to happen is phi is just going to approach 0, and the instantaneous translational acceleration vector will effectively just become the centripetal acceleration, because it will always just point towards the center of the circle. Because that 11.2 is going to stay fixed and be time independent, and this value is just going to grow into the hundreds and the many hundreds of meters per second squared. Okay, but of course it would be unsustainable to accelerate a ring indefinitely. Okay, and so the last question was a conceptual question. Based on the results of this problem, does constant alpha imply constant translational acceleration? Okay, so, or in other words, does constant angular acceleration, alpha, imply constant translational acceleration, A? And the answer is no, definitively no. In fact, constant alpha means that translational acceleration is growing and becoming more radial in direction. All right. Well, thank you.